Okay, so thank you, and it's really a pleasure to be part of this workshop and long program. I'm really enjoying the discussions and the excitement that come from them. And so I'm particularly happy to present my work to you, and the title of my talk is Enabling Fast Principles Modeling of Electrochemical Nanointerfaces under Applied Voltage. Okay, in devices such as electrolyzers or fuel cells, but also sensors, or even in bioelectronics, the fundamental processes that underlie the efficiency or the stability of the process occur in a few atomic layers. Few atomic layers at the interface between the electrode and the electrolyte under voltage. But understanding knowing, so it is very important if we want to optimize these devices and processes to understand how the voltage reshape the interface and the physical chemical properties of the interface. But this is very difficult to do, both experimentally and theoretically. And my work is, part of my recent work is trying to solve this problem and try to progress in this understanding. And okay, perhaps this is a very general slide, and say, why do we care about electrochemical interfaces? They are, electrochemical interfaces are all around us. They not only underlie energy storage, conversion, and production, but they are also involved in materials growth and dissolution. They are essential for biological processes, but also for some types of memories or for sensing, some type of sensing. And every year, trillions of dollars are invested in the optimization of these interfaces. And yet, we do not know, we do not have a molecular level view of what happens at these interfaces. And doing this experimentally, only with experiments, is difficult, because these active sites live under a condensed phase. So they are very difficult to characterize experimentally. And therefore, we need theory to help in this understanding. But also theory is a bit problematic, and still we do not have a complete theory that allows really to understand what happens at these interfaces, the role of the solvent fluctuations, and how kinetic reaction kinetics work, and how physical chemical properties are related to the microscopic structure, nanoscopic structure. And what I want to say is that all these devices share the same fundamental structure. There is a source of electrons, a drain of electrons, and something in between, where chemical reactions are coupled with a potential, an applied potential. So in all these devices, all the fundamental reactions that occur at these interfaces are share this framework. They result from the combination of applied potential, currents possibly flowing through the cell, and reaction indeed. But I said that it's a bit difficult to simulate these systems. Why it is so difficult? I mean, 2025, we want to be able to simulate a nano interface. This is because this is a prototypic electrolytic cell. They are very complex systems. First of all, we have multiple phases, and in each phase, multiple degrees of freedom, ions, dipoles, and then ions diffuse. There is an accumulation of charges at the two opposite sides of the interface. But the most defining feature of electrochemical interfaces is the presence of a highly nonlinear, non-uniform electric field. And this field is huge. It's of the order of 10 to 10 volts per meter. So we can think that lightning requires 10 to 6. Normally occur when there is a potential difference of 10 to 6. So this is 10,000 times more than the potential difference needed to initiate lightning. So it's it's an extreme condition. And this is a defining feature of what happens at the electrified interfaces. But there is no simple way to model the effect of voltage. Okay? And that is not all, because within this huge electric field...
May I make a remark there?
Yes, sure.
Because of this field, I know this argument. So, but if, for example, we plot the average electrostatic potential on a water-metal interface, then the atomic statistic, so to say, the field close to the nuclei is even much stronger. So you have, so to say, you have your slope, and then you see if you have an atomic resolution of your fields.
Yes.
Then there is even higher fields. So to say, this is on atomic level, it's not a high field.
Yes, of course, because locally...
It's on a global or macroscopic level, it's a high field, but not on the atomic level. The 1/r potential of the hydrogen molecule is much steeper.
Yeah, actually, it is about of the order of 1 electron volt per...
This argument is valid, but I just wanted to make, so to say, that when you really plot it on an atomistic scale, then you see that there's superimposed the atomic structure of this. Okay.
Yeah, so you are meaning, you are talking about the oscillation that you see within the metal.
That's right, and especially very close when there is a layered structure still, and even if you average over, so to say, then you have one.
But then you average that and you feel that...
No, this is still, because the water is still immobile, and so to say, it's... But okay.
Yes, within the metal, you have... you evaluate the macroscopic potential just averaging this field, and so this field does not have, on average, a slope, and so the force is 0. On average in bulk.
No, but the electron field is.
But locally, yes, I agree that the interaction that keeps the metal together is strong. But in this case, the field triggers.
I understand your argument.
Yes. Okay. So anyway, it's not a negligible field. It's a huge field. Yeah. And and it's difficult to model because in electrochemical reactions are stationary open boundary non-equilibrium stationary non-equilibrium processes, which are fed by the intake of electrons. Giving the electrons to a reservoir, and this electron flow sustain the progress of chemical reactions at interfaces. And indeed, this is a workshop which is about the boundary conditions. Electrochemistry is an open boundary problem. If we want to really reproduce the real electrochemical environment, we need to take care of, consider that electrons exchange with a reservoir with a certain electrochemical potential. And also from the electrolyte side, this was very, very nice illustrated yesterday, the ions exchange with an electrolyte. So the full electrochemical interface is neutral, but typically, when we simulate a tiny piece of this interface. And so when we build our simulation, we need to be able to fill both reservoirs. And there has been a lot of talking about controlling these boundaries. But my research has focused a bit not only on controlling this, but also controlling this interface, this boundary. So opening the possibility for electrons to exchange with the reservoir. And then try to do as much as possible to have a physically and thermodynamically consistent description of this part, but without solving the problem of how this interfaces with the rest explicitly. And people, various, have tried to solve this complexity, to model this complexity in a very simplified way. I mean, just using sometimes dry interfaces or very simplified interfaces, or sometimes performing calculations with no electronic structure. And typically the setting is that of using neutral and periodic cells. And so these causes, the result of this is that many quantities are not very reliably reproduced with standard computational methods or with these methods that do not include many of the ingredients that are present and contribute to defining the electrochemical transformation. For instance, to give an example, molecular coverages are very strongly dependent on the level of theory that we use. And so the boundaries of the region where hydrogen or oxygen start absorbing on, let's say, platinum vary a lot depending of if we model the surface with in gas phase, or if we model the surface with a water bilayer plus continuum solvent, a block of ice on top of it, or some water a bit more realistically described. And another example of this, which is remarkable, is the evaluation of the hydrogen evolution barrier at platinum-water interfaces. The most basic and easy reaction to model, but still the difference between experimental observation and computational prediction is huge. It's a 0.6 volt of difference. And this is huge because in electrochemistry, the current is related to the overpotential, which is related to this quantity, by an exponential, the Butler-Volmer reaction, by an exponential reaction. So a 0.6 difference in overpotential generates huge discrepancies in current density with experiment. And so my approach is to try to address all these problems. And so in particular, first of all, I tend to have an atomistic representation of the electrolyte, which is fully dynamical, fully from first principles, with the electron-ion molecular dynamics resolved, and also the voltage is controlled. And so essentially, what I call this, when I want to be fancy, is that I've generated a computational microscope that allows to have a window, to open a window on what happens at different potential conditions at an interface. And applying this, I have developed these computational tools. They are now implemented in CP2K code, and I've started applying this on problems related to electrocatalysis, corrosion, and sensing. I will mostly talk not even about electrocatalysis, but about what I've learned about the platinum water and the metal water interfaces with this, and a little bit of corrosion. And so, okay, how do I control the potential? I have developed a hierarchy of computational methods that allow to try to control the potential. The easiest, the most basic one, still work in a context of periodic boundary conditions. It is the ion imbalance. And then there are two more advanced approaches which allow to control the potential. The one in the limit of no electric currents flowing through the system, and the other which include completely the effect of the current on ion dynamics, so the so-called current-induced forces. So let's start with the most basic one. And this method is very simple, essentially, because I copied experimentalists. When experimentalists want to, let's say, reduce a nanotube in solution, they throw ions in solution. And so the effect of this is that the nanotube or the material gets some charge, acquires some charge. And the same concept is applied here. The ion imbalance methodology allows to vary the delta V, the potential difference between the bulk electrode or the Fermi level of the electrode and the electrolyte by changing the ionic concentration within the liquid. So essentially, in this method, I introduce an excess of a species of ions, let's say an excess of 2 chlorine ions over the sodium ions, which are explicitly described in solution. And so I allow the metal to charge in response. And so systems which have an excess of ions of positive versus negative correspondingly have model an electrode that is more negatively or positively charged. I will explain how does it work in a minute. But here I want to say that with this approach, one can then simulate, depending on the concentration of ions, on the imbalance of ions in solution, a variety of different conditions for the potential. And so, but one thing which is important is that the different systems that are simulated need to be aligned to a common reference level. And the common reference level is, in my case, the bulk electrolyte. Here I want to tell you, you see all these ugly black lines? These are the instantaneous potential drop averaged macroscopically, spatially, along the trajectory. Okay, so this is the time spread of the trajectories. These are huge systems, so you see the spread in time is pretty small. And also, this is a symmetric system, so, and there is a very high ionic concentration. So you see the potential drop occur in a very small space. And in the middle of the electrolyte, actually, we have flat potential. If you average that, on average, it's almost flat. It's flat, and also the charge is 0. The average charge is 0 during the dynamics. So I use that as a reference to evaluate the potential drop in a system. And then once I have a reference system that I decide how to align to the experiment, let's say I model a system at the potential of 0 charge, I evaluate the potential drop of this system, then I compare the difference, I assign the electrode, the potential to the electrode by comparing the potential drop of the different systems. And this is slightly different, but at the very end is very similar to what other people, like Rosmeisel in his generalized, that's it, I don't see the arrow, that is the problem. Okay, so, and this is, at the very end, equivalent. I don't know what happens, really. I need a new computer. To what Trasatti suggested in 1986, when he decided that it was end of the story. We know how to put electrode on an absolute scale. So in this case, the most reasonable reference was the vacuum in front of the electrolyte, in front of the metal. And that makes sense because then we know that this, okay, that is another thing. And okay, we know how to relate this to the standard hydrogen electrode scale. And so it's 4.44 electron volt. And so if we measure the difference between Fermi level and this point and then add 4.4 electron volt, we know what is the absolute value for the electrode potential. But what I do is essentially assuming that this level is flat, that we are at convergence with the potential drop with in the cell. At the very end, the difference between this and this point is just a constant, and the real physics or chemistry at the interface is determined by the difference in potential drops in different systems, so by the different slopes of the voltage of the field. And this problem solve and adopting a solution where one relates the electrode potential to this point. This would be the galvanic potential of the platinum-water interface. Solve some problems, some issues in convergency of this interface. For instance, so essentially we would spend a lot of time in equilibrating this interface just to have a value which is of this step, which is reliable. But beside that, it's completely equivalent, it's not a problem. And so why my methodology of throwing an imbalance of anions or cations in solution work? It's all about energy level alignment. If the DFT scheme is good enough that the levels, energy levels of the anions, cations, and metal are properly aligned, then this allows the Fermi level to the metal to charge. So let's say, for instance, if the sodium, I add the sodium which is in solution, a neutral atom, and then the determination of the charge of each species in solution is determined by the occupation of the energy level according to the DFT scheme. So if I don't control that, I don't know what happens there. So look at the green. And so this would be the correct energy level alignment for a sodium ion in solution. So you see the HOMO would be above the overall Fermi level of the solution. And so this means that this level would be empty, and the charge would go to the platinum. And so this means that the sodium would leave in solution of a sodium plus atom, as it should be, and the metal would be charged a bit more negatively than if I add a chlorine, where the SOMO is below the Fermi level. And so it requires, because it wants to be occupied, an electron that would come from the metal, okay? So this is the mechanism that allows to. So now I do not see Giulia Galli, but she would have scolded me, because this difference, of course, is not the 10 electron volt difference that the water is here. It's outside here, but the difference between HOMO and LUMO of water is not the 10 electron volt, electron volt that we would expect with a perfect and realistic description of water, but because this is a PBE, so it's about 6. But still, the energy level alignment and the trend is correct, and this is what we could do at the time. And that at the very end, I don't aim at having a realistic description of the ions in solution. I merely use the ions to charge the interface, and so that is the approach. Okay, so what is the first application of all of this? It's platinum water it's platinum, the most fundamental interface. So we know this is a very important problem because the global hydrogen market is increasing, it's predicted to grow even more, and more than 80 million tons of hydrogen per year are already produced by electrolyzers, but still we want to improve them. And for instance, in alkaline electrolyzers, so still we do not understand how to, why the reaction is so sluggish. And so if we want to understand the reaction, how to improve this electrolyte, we need to understand the mechanism. And what do we know experimentally about this, about platinum-water interface? we know that, okay, this is state-of-the-art IV curve for platinum water. So we see there is this region, which is a double-layer region, where there is no ion absorbed in solution. And this is around the potential of zero charge. So here. When we go down towards the negative potentials, we know that hydrogen atoms experimentally start absorbing over the surface. And in particular, there have been hypothesized two species of hydrogen absorbed over the surface. The overpotential deposited hydrogen, which is at lower potential, so over the potential where hydrogen starts evolving. And this is thought to be involved in the hydrogen evolution. And the overpotential, so this should be underpotential deposited hydrogen, which starts building on different sites at lower potential. But what is the interplay between these two species is unknown. And another related problem is to understand, Jun Chen spoke about the problem of the origin of Helmholtz capacitance in the limit of very high ionic concentration. The Helmholtz, so he focused on ion capacitance and in the limit of very high ionic concentration at the interface. I do not have this constraint. And so I would like to understand what is the origin of this peak, why it starts, where it starts exactly. And this cannot be understood by the classical theory. I mean, Guy, Chapman, Stern predict a constant. There is a Gellium model, as Jude explained yesterday, which is bell-shaped but is qualitative, does not have information about the electronic structure of the system. And so all these two problems are related. I hope I will show you soon. And so they are all related to this question. How does voltage control absorption, surface properties, and capacitance? And with this methodology that I've developed, it is possible to really have a window of what happens at the interface at different potential conditions. So in this graph, I have plotted the absorption energy of hydrogen over the platinum surface. And we can see that, and I also evaluate the coverage as a function of the potential. And it can be seen that this coverage, building up of coverage, is predicted correctly from zero coverage at potentials around the potential of zero charge, building up to full coverage or almost full coverage at lower potentials. But we can also reproduce the hydrogen absorption-desorption current, which matches with the experimental prediction. But we can do even more, because we can resolve and observe for the first time computationally the two species of hydrogen absorbed over the surface and their interplay. Here you see in this graph, we see that there is a complex interplay of the two species of hydrogen. In particular, we have the underpotential deposited hydrogen, which starts building at higher potential and is typically absorbing over FCC sites of the metal. And the overpotential deposited hydrogen absorbs on top position. But the surprising thing is that you would expect that since, hydrogen can have a little bit of charge, they would repel each other and would tend to maximize their distance. But actually, they clusterize. And they have dynamic clusters that laterally organize in a way that the coverage stays constant, but the shape of the cluster, they are together, and the shape of the cluster varies during the dynamics. And we see that the predominant cluster is first the UPD, and then this is around the hydrogen evolution reaction, it's substituted by OPD, by Jakob.
May I ask, how big is the size of the supercell that you can see this kind of effect?
It's about, about 50 platinum atoms per layer.
50?
50 per layer. So it's about 15 by 15 angstrom, something like that. And then there are 30 angstrom of water on top of it. And yeah, so it's a huge system. I mean, this, and I've simulated this for 50 picoseconds each potential after equilibration, meaning that the number of chemisorbed species during the dynamics doesn't change. So the charge over the electrode doesn't change because of desorption or absorption processes during the dynamics. And so this is very interesting because it says that the apparently innocent platinum interface contains, has a nanostructuring, already the ideal flat interface. And then it allows also to answer the question, how voltage affects the wettability? Because when there is hydrogen over the surface, and by the way, the two species always coexist at all potentials, okay? When there is hydrogen on this potential, water cannot really chemisorb over the surface, as Mira explained in her talk. And water is repelled and points hydrogen down towards the surface. So there is a hydrophobic configuration of the surface. Whereas at higher potential, water can get closer to the interface, pointing oxygen down, and so there is essentially an hydrophilic phase. And so we can see that the voltage-driven chemisorption, so there is a voltage-driven wettability flip from hydrophobic to hydrophilic on the surface. And the most interesting part of this is that there is also a change in primary polarization mechanisms around the potential of zero charge. Because when we compare the water coverage and orientation at different potentials, we see that water always chemisorbs in these flat configurations with the dipole almost parallel to the surface, and the number of chemisorbed water molecules, always in the same configuration, increases with potential. Whereas the water reorientation is only due to the second water layer. And this water, it's also charged, and each water molecule carries about 0.1 electron per molecule. And so when the potential changes, the chemisorption dipole induced by this charged water molecule increases steeply. And so if we plot the charge, we see this sigmoid, which reflects that the change in primary polarization mechanism. So in this region, there is hydrogen, and water cannot absorb. Here, water can start absorbing, and then with this polarization, chemisorption, strong polarization dipole that increases with potential. And then at some point, it saturates. And if we do the derivative of this charge, we get the differential capacitance that magically exactly reproduces the experimental capacitance, bell-shaped differential capacitance. Okay, so also we can learn about lateral interaction, and we can also do whatever we want about, we have all the information about the interface. So for instance, we can calculate some frequency generation spectra for this metal, and this was done in collaboration with Jair Littmann, and where we evaluated the vibrational SFG spectra and show that the charge in signal intensity and vibrational frequency correlate directly with the charge of water structure at the interface. Okay, I hope I have convinced that with this methodology we can learn a lot about the interface, but of course an ideal interface is very far from what is the real multiparticulate that exists and catalyze a hydrogen reaction. So a certain research line is on trying to understand more realistic interfaces with even larger model systems. that explicitly include low coordination sites and interfaces between different facets on the interface. And in particular, this model that we have developed reproduces almost exactly, at least in this region that I've represented, what is observed if you cycle voltammetry platinum water interface repeatedly. At some point it saturates to this configuration where there are islands which are separated by about 1 nanometer of well, and the terraces are a bit like 10 times larger than this. But this is very similar to the real system that is observed experimentally. And so with this, we could understand a little bit more of the role of the edges at this interface. And so we understood, first of all, that this edge at potentials where in the flat surface we would expect to be covered by hydrogen is actually covered by water. And the water-platinum couple, it's all positive. And therefore, since the edge is fully covered by water, this edge is very positive. Okay, it's much more positive than the rest. And the consequence of this is that if we evaluate the contribute of the basal plane or the edge to the differential capacitance of the interface, we can see that the main contribution to the differential capacitance comes from the basal plane, because the edge is already saturated with water, so it doesn't change with a different amount of water. And also, we evaluated, what is the decay of the charge? This is in each row of atoms. So we see that there is a decay, and in the middle of our cell, we recover the condition for the charge of the platinum, which is expected in a flat, ideally flat surface. And the electronic signature of this charge localization is a local potential drop, which, if we measure it in the direction coming out of the edge, so this would be the black line, or getting in the middle of the cell. I mean, if you continue this, actually it ends up here. You see that there is a local potential which is higher, consistently with a more positive charge. And there is a signature of this also in the position of the very center of the D band, where the projected dose over the edge atoms has a D band which is higher, closer to the Fermi level, than the D band of the flat interface. And so this generally correlates with higher reactivity. It's also more peaked. So it's interesting because there is a higher reactivity of the edge. Still, we didn't simulate the reaction, but we can have we can start learning why the edge is more reactive in this case. And so this is, yes, about the phase diagram for the system. It's about that shows that the potentials which are around the potential of zero charge, the system ended down to minus 0.4 around the potential of zero charge, the edge is fully covered by water. So this is another striking difference, because the potential is more positive. And so oxygen starts absorbing a bit earlier. Just a note, if you calculate the surface in vacuum or in water, this is with the full water layer, the charging of the edge is the opposite. So we really need water and to achieve that description. Another example, okay, so this is about platinum. Another example of how changes in voltage dramatically alter the fundamental properties of an interface. It's with another work that we are almost sending out with the PhD, Rashid Al-Aidous, and it is about aluminum. Aluminum is very important for corrosion. Your watch is was made by aluminum, but then it started corroding and they changed it. And so we want to understand, and it is very important for planes, so we want to understand what is the fundamental mechanism leading to the formation of the protective layer of the oxide over aluminum. And the very interesting thing applying this methodology to aluminum is that the phase that is formed above aluminum is strongly dependent on potential. So we see that at lower potential, there is around the open circuit potential, we have the nucleation of an ordered alumina phase, which compare really with, I think, alpha alumina. I mean, these three layers. And essentially reproduces some TM experiments that could be done at this potential. But we can do more than that because we can see how that description changes with potential. And we see that at higher potential, there is the growth of an amorphous oxide growth. Here I, of course, limit myself to the first step of aluminum oxidation, but that is already interesting, that the potential has initiate different phases. And so potential could be used to control the phase that is growing.
What is the time scale for these processes? Are you doing it by first? I mean, can you get it by first principle?
It's about 60 picoseconds. This was a huge project. It was 22 different coverages. I compared 22 metastable configurations with different coverages, and the system evolved spontaneously to this configuration and then stayed stable for the time I've sampled the trajectory. And because, I mean, the interface properties converge pretty quickly. The problem is with the convergence of the ions above it. But if you only focus on the formation of the immediate water-aluminum interface, it's pretty quick. I mean, essentially, our starting configurations was a set of configuration with either hydroxyl oxygen or oxygen plus hydroxyl configuration, just chemisorbed over the surface, and they spontaneously evolved in this and stayed there. So I assume that is a metastable state. And then I compare the energetics. You see each of these lines, it's a system that we have simulated, and the slope is the number of electrons that are exchanged to absorb each of those species. And so you see that this is the phase diagram profile. Yes. So I find that is very interesting, that you can control the phase of the oxide state with the potential. Okay, so I have 10 minutes just to show you the next level of my description of the potential. So we see that with this approach, which is very basic, can be implemented in periodic boundary conditions code, we can model physical properties and corrosion mechanisms at interfaces, and we can describe essentially metastable equilibrium state, provided that during the dynamics there is no change of charge over the electrode. So it requires a little bit of work to prepare good systems, but that is what we can do. But that is not how essentially experiments work. Because in the real experimental setting is open boundary with respect to the electrons. So if we still keep modeling our interface with periodic boundary conditions, essentially there is this problem we cannot circumvent, that the Fermi level is the same across all the interface. So we can circumvent, but we need to work a lot to circumvent this problem. And so if we focus, for instance, on the reaction pathway for charge transfer processes, we can see that if we do not allow to the electrons to get in and out of the cell in the proper way and exchange with the reservoir, these profiles change during the charge transfer process, because there is some charge that is moved over the electrode, and that shift the level while this charge transfer process occurs. So this is at the origin of the issues with the evaluation of activation barriers in interfaces which are biased with potential. And so essentially, we would like to have a system that, at least from this side, is able to keep this level constant during the electron transfer reaction, so that when one electron leaves the surface, this level stays constant because it's replenished by an electron that comes from the reservoir. And this is precisely what this methodology, which is named the airy probes, hairy, really, very tiny probes, hairy probes DFT, which allows to control really the potential at the at the boundary of your cell. And so how does this work? Essentially, you attach tiny probes to whatever region of your system you want to, and every probe can be characterized by a certain electrochemical potential. And so in this way, according to, this is a very, this derivation comes from the Liebman-Schwinger scattering theory. And so it's accurate. And the interesting thing is that in the small coupling limit, so in the limit where there are no electric current through the cell, in the limit where the electrons are, so that the rate limit in transfer is determined by the ionic dynamics that occur at the interface rather than by the electron transfer rate from the interface to the reservoir, which typically applies in electrochemistry. We can really simplify the theory, which is based on non-equilibrium green function theory, in a way which is very elegant. So essentially, this Hairy propagator, which controls the local Fermi level, translate into controlling the occupation of the changing the stationary non-equilibrium occupation of the states, and the recipe to obtain the new occupation, instead of using the standard Fermi level, Fermi function, is obtained by doing a combination of Fermi level functions centered on each atomic orbital, weighted by the coefficient of that atomic orbital in the system. So why I'm saying all this bit complex thing? Just because all these quantities, the coefficient in the density matrix, of a function of the density in the localized basis set that is being used, and Fermi function, we know the Fermi function, they are all present in the cell in our codes. They are all calculated at each of the cell consistent step that allow to minimize the electronic structure of the system. And therefore, with this approach, we can essentially perform DFT molecular dynamics under bias at the same cost of DFT. So, which is remarkable, because normally with the standard molecular electronic approaches, it takes 1 order of magnitude more. And so what we can do with this, we can have a lot of flexibility, because we can change the potential, really fine-tuning it. And so with very small cell, we can reproduce, the fact that water, chemisorption in a certain configuration as a function of potential, and the platinum around it becomes more negative than it used to be. The platinum, all the properties, properties of water chemisorption are reproduced. Also, that when we change the potential and go to low potential, we see that spontaneously water fly away. That is not anymore the stable configuration. So if we keep using a configuration obtained for neutral systems to model systems which have a potential, we are not modeling the equilibrium configuration for that system at that potential. And indeed, the important thing is the absorption energy and structure. So also absorption energy and structure, even for non-electrochemical step, for water absorption, change with bias. So we can see there is a curve of the most stable configuration has 8 water molecules, or 12, so the structure changes and the energy changes in a non-obvious way, okay? So we have to say that, therefore, this proves, I hope, that reliable electrochemical data requires simulation with explicit voltage control, even for the basic evaluation of absorption energy, let aside the reaction. And another element that is very important to control here is that, because here we have described only one aspect, so the fact that the electrons are sent to the right reservoir in the system, but actually what we are interested in is also that this potential drop is properly defined. So we need to be very careful that this water level in the middle is well described. And in our case, I mean, it was well described and robustly reproduced, because when you change the potential on the two sides, the water level doesn't change, so it's robust. But when you model reactive processes, perhaps that is a bit less obvious, but you can add the probe here, and so that could be the solution. I mean, just to gate that electrode as you wish. And so you can solve the problem. I will just say very quickly that we did also the full implementation with non-equilibrium grain function and CP2K. So again, there is this structure where the system is partitioned in 3 regions, and we have a scattering region, which includes the source of scattering where the potential drops plus a little bit of the electrode, and then 2 semi-infinite leads that allow to send electrons to the right reservoir. And within the non-equilibrium green function formalism, I mean, the flux of current going in and out of the cell are taken care of. And so we can evaluate the non-equilibrium properties in the middle of the cell and evaluate currents, for instance, through the cell. And we implemented this in CP2K, which now has electron transport functionality, and also implemented non-equilibrium stationary non-equilibrium current-induced forces, which are extremely important to understand electromigration processes, dendritic growth, and even membrane processes where a wire, even in flat interfaces, can grow or dissolve due to the presence of a bias applied at the interface, and perhaps also helped by the transfer of momentum from electron to ions that go through the wire. Okay? And that's it. This is a signature of the difference of a wire, of the transmission coefficient of the wire, either in vacuum or in water. You see there is a difference. So the behavior of this wire is different if there is water or not. And that is the summary that, very quickly I have identified for the first time computationally the 2 species of hydrogen over platinum. That I've shown that electropolarization is associated with a change of coverage of charged water molecules. I've shown that the onset of peak in differential capacitance is due to the electronic response of interfacial water to the increase of potential. I've illustrated my hierarchy of methods that I've developed to model the effect of the applied potential by charging the electrode, or in the limit of no currents, or the heavy load with everything in it. And I hope I have convinced you that potential-induced surface polarization significantly impacts the structure of the interface, and we really need that. Thanks to my group, I've illustrated this. There are also many other applications, and this was my group at the peak of its population at Imperial. Thank you for your attention.